Hello. The paper presented in this lecture is the result of a joint work with the professors Carballosa, Granados, Mendez Bermudez, and Pestana. I'm going to speak about some topological indices, which are a tool that maths offer to measure, or even better, predict some chemical or biological properties of chemical compounds. And I'm going to focus especially in one of them, the arithmetic geometric index. Chemical graph theory is a branch of mathematics that started in the 18th century, and here we have possibly two of the fathers of the theory. On the one hand, William Cullen was a Scottish chemist who, since mid-18th century, used what he called affinity diagrams in his lectures in order to represent forces supposedly existing between pairs of molecules in a chemical reaction. On the other hand, Arthur Cayley was probably the first to publish results that consider molecular graphs as early as in 1874. He used this concept for the purposes of enumeration of isomers. Cayley considered diagrams made of points labeled by atoms and connected by links into an assemblage. His collected mathematical papers contain 967 papers. This number has only been exceeded by Euler and Cauchy. A molecular graph, or a chemical graph, is a representation of the structural formula of a chemical compound in terms of graph theory. Graphs are generated from molecules by replacing atoms by vertices and bonds by edges. Usually, we are going to use molecular graphs to refer to hydrocarbons, that is to say, organic molecules which consist only of carbon and hydrogen, and usually hydrogen will be suppressed. So, in our molecular graphs, vertices will refer to carbon atoms and edges will refer to bonds between carbon and carbon. A topological index is one single number. This number represents a chemical structure in graph theoretical terms via the molecular graph, and it correlates with various physical properties, chemical reactivity or biological activity. It is used to understand physico-chemical properties of chemical compounds. So topological indices are interesting since they capture some of the properties of a molecule in a single number. Next, I'm going to define several of the most famous topological indices. I'm going to start with Wiener index. This index is defined as the sum of the lengths of the shortest paths between all pairs of vertices in the chemical graph representing the non-hydrogen atoms in the molecule. It is named after Harry Wiener, who introduced it in 1947. At the time, Wiener called it the path number. It's the oldest topological index related to molecular branching. Based on its success, many other topological indices of chemical graphs, based on information in the distance matrix of the graph, have been developed subsequently to Wiener's work. It's been proved to be closely correlated with the boiling points of alkane molecules. It also correlates with density, surface tension, viscosity, and perhaps more interesting from a different point of view is that it's been frequently used in sociometry and the theory of social networks. This number is used, for example, to identify the influencers or individuals who should be vaccinated in the first place in the event of the outbreak of an epidemic. The next topological index that we are considering is Randich index or connectivity index, defined this way. Here we have the two isomers for which we computed before the Wiener index, and if we compute the Randich index for them, this is what we get. Well, the suitability of the Randich index for drug design was immediately recognized. However, the physical reason for the success of such a simple graph invariant is still an enigma, although several more or less plausible explanations were offered. During the next 20 years after it was defined, this graph invariant did not attract any attention of mathematicians. Then Erdős, one of the most distinguished mathematicians of his time, together with Bolobás, published their first paper in 1998. Then the mathematical and mathematico-chemical community recognized that the Randich index is worth studying. and a flood of results and publications studied. There is no doubt that the Randich index is the most studied, most often applied, and most popular among all topological indices. Our next index is the geometric arithmetic index. In this index, as you can see, the numerator and the denominator of each term are the geometric and arithmetic means, respectively, of the degrees of the end vertices of an edge. Since the numerator is less than or equal than the denominator, each term is at most 1. Well, in general, the reason for introducing a new index is to gain prediction of a target property or properties of molecules, which is somewhat better than those numbers obtained by already present indices. The properties of octanes are commonly used as a standard for testing new topological descriptors. Well, the predictive ability of the geometric arithmetic index, which, by the way, was introduced in 2009 by Vukcevic and Portilla, and here we have the geometric arithmetic index calculations for our two isomers, butane and isobutane. As I was saying, the predicting ability for the geometric arithmetic index is reasonably better compared to Randich index for some physico-chemical properties of octanes, like the boiling point, the entropy, the enthalpy of vaporization. And finally, the last two indices that we are presenting are the arithmetic geometric index and the ISI index, the inverse sum index, which is defined this way. Both were defined recently in 2010 and in 2015. This ISI index has a good purpose for its definition, and it's that it's the best of all predictors, the best one in estimating the total surface area for octane isomers. We have mentioned in several occasions octane molecules. Well, the general formula for octane is C8H18, 8 atoms of carbon and 18 of hydrogen. This is one possible representation, and simplified we would have something like this, or even better, when we suppress the hydrogen atoms, something like that. Well, there are 18 octane isomers, which are these ones, and one of the most important ones is precisely this one, the isoctane. Well, the isoctane is the reference point 100 in octane rating of gasoline. Regarding the predictive power for boiling point of octane isomers, when we compare the geometric arithmetic and the arithmetic geometric indices, it happens that the first one has a better correlation, a better predicting ability. But when we are studying the entropy, it's the other way around. In this occasion, the arithmetic geometric performs better. That's why we need both, okay? Both indices are necessary. Next, I'm going to present one of the main results of the paper. Although the proof is quite technical, I'll give an informal outline of it. This result establishes a comparison between the arithmetic geometric index, recall that this is the definition, and the ISI index. The first one, so the result says that the first one is always upper bounded by a constant times the second, and the constant depends exclusively on two invariants of the graph, the smallest and the largest degrees of the graph. We will denote by little delta the smallest and by capital delta the largest. Furthermore, the inequality is sharp, and the bound is attained either by regular or biregular graphs depending on the value of this constant. That's to say, when the maximum between these two quantities is attained at the first term, then the equality is attained when the graph is regular. When the largest, the maximum of these two numbers is attained at the second one, then the equality is attained for biregular graphs. When both are equal, obviously the equality is attained by regular or biregular graphs. So the equality is attained for regular or biregular graphs, but what's that of a regular or a biregular graph? Well, a regular graph is one in which all the vertices have the same degree. That's to say, each vertex has the same number of neighbors as the others. Here we have two examples of a two regular graph where every vertex has degree 2, or a three regular graph where all its vertices have degree 3. And Peterson's graph is just a famous example of the three regular graph. And a biregular graph is a bipartite graph. That's to say, the vertices in the graph can be split into two sets, the red and the blue in my example. And all the vertices in each partition have the same degree. That's to say, for example, all the red vertices have degree 3 and all the blue vertices have degree 4. Although the proof is quite technical, as I said, I'm going to give an intuitive idea of the proof. So first of all, we define this domain on the plane determined by the invariants of the graph, little delta and small delta. Recall the minimum degree and the maximum degree in the graph respectively. And over this domain, we define the two-dimensional, the two-variable function t, capital T, this way, with this by means of this expression. Well, for a fixed y value defined on the interval from little delta to capital delta, for example, for this arbitrary fixed value of y, it's easy to check that the partial of t with respect to x is a decreasing function, and therefore t is always upper bounded by the value of the function when the first variable is fixed to be little delta. That's to say, for this fixed horizontal line, the largest value is attained on the left of the segment and the smallest value is attained on the right. So for arbitrary y values, the largest values are always going to be attained on the pink vertical segment. Using this idea, taking this into account, then we define a one variable function for the fixed value of x equal to delta in the function t. So this one variable function r happens to have this expression. Recall, the only thing that I'm doing is replacing x by the fixed and constant value delta. Well, for this function that we've just defined, it's easy to check, well, it's not that easy, it's technical, to check that the maximum value of this function is attained at the endpoints of the interval of definition. That's to say, the largest value along this line for this one variable function is always attained either at this point or at that point. So in summary, the function, the two variable function t, is always upper bounded by the function t when x takes the value little delta, and this function is in turn upper bounded by the maximum between these two quantities, which means that if we consider the function t over this domain, the largest value, the maximum, actually it's attained either at the point p, which corresponds to the function t evaluated at little delta, and or the point q, which is obtained when the function t is evaluated at little delta, capital delta. Recall that this is the inequality that we want to prove, and this is what we've got so far. The function t that we defined at the beginning of the proof is upper bounded by the maximum between these two quantities, which happen to be these two expressions. So the next thing is to consider for every edge uv in the graph G, evaluate this function t at the degree of u and the degree of v. So if we just evaluate the function at these two quantities, we get this expression. And this expression can be written as the product of this red and blue factor. We write it this way to simplify the calculations later. And according to this inequality, this quantity, which is the evaluation of t at the UDV, recall, is upper bounded by this quantity. Okay, now let's consider this inequality, okay, and solve for the red factor. If we do it, I get that this red factor is upper bounded by the maximum between these two quantities and this expression. But the red factor happens to be the density of the arithmetic geometric index, and the blue factor happens to be the density for the ISI index. So, finally, we have proved the inequality that we wanted to prove. And that's all. Thank you very much. Bye-bye.